everybody, welcome back to chemistry. And so now what I want to do is talk about some properties of the liquid state. And so what I want to do is talk about something called evaporation, condensation, vapor pressure, and boiling point. So the first thing I want to do is talk about evaporation. So I think you all kind of know what that is. And so here, let's say you have a dish of water outside, and let's say this dish of water is uncovered. And so we have all the water molecules as blue dots down here. And also I've kind of drawn in air molecules as purple or pink dots. And so I think you know, if you have an uncovered dish of water outside standing out for long enough time, that eventually all the water evaporates off and there's no more water here. And so let's think about in detail how this happens. And so what happens is, for some of these water molecules on the surface here, what will happen is some of these water molecules will be able to absorb enough heat where they will be able to break out of the liquid phase and then go into the gaseous phase. And so this slowly happens over time. And so here's one water molecule that goes, and here's another, and then on and so on. And so these water molecules just slowly but surely break off, and they go off into the atmospheres. And so this is the process of evaporation. So what I want to do is write an equation for evaporation. So I'm going to do that here. So this is evaporation. And so here, I think you can see is that the reactant here is a water molecule in the liquid phase. And it's becoming a water molecule here in the gas phase. It's up there in the air, right? And so maybe one of the things that you kind of notice is that here the liquid water molecule must absorb energy so that it has enough energy so that it can go into the gas phase. And so this is an endothermic process. So let me write here, this is endothermic. And so to remind myself that this is endothermic, I'm going to put an energy term, an E, on the left side of the equation here. So this is an equation for evaporation. Okay, sounds good. Now, let's say that you decided that what you wanted to do was you wanted to cover this dish with a piece of glass. It could be something called a watch glass that will cover the dish. So we have covered this dish, and we have water molecules down here. And so again, we're going to have evaporation like we had before. So here's another one that is evaporating up into the gas phase. But then what will happen is that maybe a molecule in the gas phase here, it might return to the liquid phase. And so this process where the water molecule is leaving the gas phase and is going into back into the liquid phase is called condensation. So I want to write an equation for that. So we have condensation, and here is the reverse reaction. You have water in the gas phase, and it's returning to the liquid phase. Now here's something to think about. We know that here a liquid water molecule must absorb energy from the environment to become a gaseous molecule. So this is an endothermic process. And so if the reverse happens, this gas water molecule must lose heat or energy into the environment so that it becomes cool enough so it can return back to the liquid state. So if you have a gaseous water molecule returning to the liquid state, this is going to be an exothermic process. So I'm going to write exothermic here. And then what I want to do is remind myself that this is an exothermic process. I'm going to put a plus E like that here. Okay, so you can see that here in this covered dish of water, we have evaporation and we have some condensation. Now, what will happen over time is that maybe you start out with a relatively high rate of evaporation. You're putting water molecules up here, but eventually the rate of condensation will become the same as the rate of evaporation. And so when the rate of evaporation is the same as rate of condensation, then you have achieved an equilibrium. So now a way we can analyze the equilibrium is by sort of understanding how many water molecules are up here along with the air molecules compared to the water molecules in the liquid. Well, compared to the trillions and trillions and trillions and trillions of water molecules in the liquid, you only have a few water molecules up here. But these water molecules are there. They're here along with the air molecules. And you probably know at this point that the air molecules are putting pressure on the sides of the dish. And same thing here with the water molecules here in the gaseous state. The few here are also putting pressures on the side of the dish. So here, this water vapor in the gaseous state, again, is putting pressures on the side of the dish. It won't be as much as the pressure that the air molecules are doing, but it's putting some pressures on the side of the dish. And so this is called the water vapor pressure. Now, what I want to do is kind of give you a sense of the magnitude of the water vapor pressure. So again, mostly what we have up here are air molecules. And so if this is at sea level, then the pressure you might expect here from the air molecules is 760 millimeters of mercury, which is 1 atmosphere. So it kind of raises the question, what is the pressure due to these few water molecules that are up here in the air? What is the water vapor pressure? And at room temperature, it is around 25 millimeters of mercury. So you can see that the pressure that the water vapor exhibits here doesn't really compare much to the air molecule pressure, but it's fairly significant. So really here, we can figure out, if we wanted to, a total pressure. And so the way we would figure out the total pressure up here is by adding up the pressure from the air molecules with the water vapor pressure. And so the total pressure here would be 785 millimeters of mercury. So the key thing I want you to understand is that if you have water in a closed container, you will also have a little bit of water vapor along with the air molecules, and it exhibits some pressure. So what I would like to do is increase the slide and talk a little bit more about that. So an important point I need to make here is that the amount of vapor pressure you have above a liquid is going to be dependent on the temperature. And so the dish experiment I was just kind of mentioning before was we were imagining it at room temperature. And so at room temperature, the amount of vapor pressure of the water above the dish of water was about 25 millimeters of mercury. But as you increase the temperature of the liquid, the vapor pressure will increase. And so we have that graphed here. And so I want you to notice here that on the x-axis, we are graphing temperature, and then on the y-axis, we are graphing vapor pressure. So on the glass bore, I was imagining we're at room temperature. So room temperature is about 25 degrees Celsius. And so at 25 degrees Celsius, we can figure out here, we're at about at 25 millimeters of mercury pressure. But I want you to notice that as we increase the temperature, say, to 40 degrees Celsius, then we're at 50 millimeters of mercury pressure. When you're at 60 degrees Celsius, then you're at what, 150 or maybe more millimeters of mercury? When you're at 80 degrees Celsius, it's even greater, maybe about 375 millimeters of mercury. So as we go up in temperature, the vapor pressure just gets higher and higher and higher. So one thing that's an important fact that you need to know is you need to know when is it that a liquid boils. And so what I'm about to say is not only a rule for water, but is a rule for other liquids as well. And the rule is this: when the vapor pressure of the liquid matches the atmospheric pressure, then the liquid will boil. So as you know, atmospheric pressure at sea level is about 760 millimeters of mercury. And so we might ask, when is it that the water vapor pressure has that high amount of pressure? And so here we go up to 760, and we find at 760 millimeters of mercury, water will have that very high vapor pressure only when the temperature of the water is at 100 degrees Celsius. And at that point, where the vapor pressure above the liquid is the same as atmospheric pressure, then that liquid will boil. So I want to explain this on the glass board. So if I can reduce the slide. Okay, so what I want you to do is imagine that we have 3 beakers of water. So here is the liquid water here, and we have liquid water at 90 degrees Celsius. We also have some at 95 degrees Celsius, and then we also have some here at 100 degrees Celsius, which you know is the boiling point of water. So let's talk about some conditions that this water is under these various temperatures. And so you can use that curve to figure out if you have water at 90 degrees Celsius, what is the vapor pressure of the water just above the liquid? And it is 525 millimeters of mercury, and that is below atmospheric pressure, which at sea level is 760 millimeters of mercury, and so the water will not boil here. Now, when we raise the temperature of the water to 95 degrees Celsius, as you might imagine, its water vapor pressure increases. So now we're at 634 millimeters of mercury, which is still below 760, so we won't really get any boiling. But when you're at 100 degrees Celsius, then the vapor pressure of water vapor just above the liquid is 760 millimeters of mercury, which matches that of atmospheric pressure, and so this water boils. So it kind of raises the question, why is it in boiling water we have bubbles form and they don't break and you see boiling? Well, let's think about first what is going on at 90 degrees Celsius. So maybe one of the things you've noticed is that if you have water at 90 degrees is that you'll have bubbles form maybe at the bottom of a beaker of water, but then they'll break off and they collapse. And so let's talk about why that happens. And the reason is this. The reason why bubbles form is because some of these water molecules in the liquid will absorb the heat, and then they will transition into the gas phase. Now, here we have water here in the gas phase in the bubble, and so it's exerting a pressure on the sides of the bubble here. And so the pressure it's exerting is going to be the same as the pressure that the water vapor has above the liquid. So it's 525 millimeters of mercury. But how about atmospheric pressure? How does it affect all this? Well, atmospheric pressure of 760 millimeters of mercury is pushing down on the surface of the liquid. Now, there's a rule in physics you'll learn about. It's called Pascal's law, and it says if you have some kind of external pressure pushing on the surface of a liquid, that pressure is transferred throughout the entire liquid. And if there's a surface in the liquid that forms, that atmospheric pressure will be applied to the surface of the liquid that forms here. And the surface in this case is the bubble surface. And so here, although it's 525 millimeters of mercury inside the bubble, outside of the bubble, it's going to be 760 millimeters of mercury. Again, because that is transferred by Pascal's law. And so you can see the pressure outside the bubble is greater than inside the bubble. So when the bubble breaks off, then the bubble collapses and then you don't have any boiling. So here you can imagine the bubble here is going to last a little bit longer because now here the water at 95 degrees Celsius, the vapor pressure inside this bubble is higher. It's 634 millimeters of mercury, and so that's pressure being pushed out toward the inner surface of the bubble. But again, by Pascal's law, on the outside of the bubble is atmospheric pressure, which is 760. So when this bubble breaks off, it will eventually collapse. And so now you can sort of see why water boils, is that at 100 degrees Celsius, the water is hot enough so that it'll have a high enough vapor pressure within the bubble to be 760 millimeters of mercury. And so that is the pressure that the water vapor is pushing on the inside of the bubble. But here on the outside of the bubble, again, is atmospheric pressure, which is 760 millimeters of mercury. And so here, the bubble can remain intact because the pressure inside is the same as the pressure outside. The bubble remains intact, and the bubble goes up, and it bursts when it hits the surface of the water. So that's why water boils at 100 degrees Celsius. It's because only at that temperature, then you have vapor pressure inside the bubbles of the water that matches the atmospheric pressure so that the water bubbles can stay intact. So if I can increase the slide. So this slide points out that different liquids have different boiling points because they have different shapes of vapor pressure curves. So let me just point out that here we have a number of different molecules vapor pressure curve plotted. And so again, we have temperature on the x-axis and we have vapor pressure on the y-axis. And so the blue curve here, which I'm pointing to, is the curve for water. And so here we have a dashed line here, which I'm going to highlight. This line is atmospheric pressure, which is at sea level 760 millimeters of mercury. And you can see that the water vapor curve here intersects atmospheric pressure at 760 millimeters of mercury at boiling point at 100 degrees Celsius. But you can see, for example, there are liquids that boil lower in temperature than water, and then there are liquids that boil higher in temperature. So for example, a liquid that boils lower in temperature than water is this one here, diethyl ether. Its curve is in purple. It's right here, and so you can see the shape of its vapor pressure curve is steeper, such that it will get to 760 millimeters of mercury, which is atmospheric pressure, at a much lower temperature. And so we can see diethyl ether really kind of boils around room temperature, okay? But then there are liquids that boil at higher temperatures. So for example, you probably have heard of antifreeze, which is called ethylene glycol. That's this orange curve here I'm pointing to here. And so the orange curve here meets with atmospheric pressure at this temperature, which appears to be about 170 degrees Celsius. So it boils higher than water. And so I just also want to point out here, the reason why these liquids have different shapes of vapor pressure curves is due to the different kinds of interactions between the molecules. So with diethyl ether here, the purple one here, what I'm pointing to here, it boils at a relatively low temperature because the interactions between the molecules are not that strong. So as I recall, diethyl ether will have, of course, dispersion. It will, of course, have dispersion interactions, and it'll have some dipole-dipole interactions, but that's it. So water boils a little higher because there are stronger interactions between the molecules. So water has dispersion, dipole-dipole, and hydrogen bonds. And here we have ethylene glycol, which boils at an even higher temperature. It also has dispersion, dipole-dipole, and hydrogen bond interactions between the molecules, but there is a greater density of hydrogen bonding between the molecules, and so that's why its boiling point is higher. So you might be wondering what this is. So this is liquid mercury. You probably know that mercury is a liquid at room temperature, and so you might be curious as to the temperature it boils. And so we can check here, its vapor pressure curve. It appears to be that the mercury here has to be at about, what, almost 350 degrees Celsius for its vapor pressure curve to get up to atmospheric pressure, which is 760 millimeters of mercury. And so you might ask, well, why is mercury so high? Well, that is due to metallic bonding between the metal atoms, and we don't really cover that in this class. So we move on. So I want to just kind of reaffirm here that as liquids go, water has a relatively high boiling point, and it's because not only do you find dispersion interactions between water molecules and dipole-dipole interactions, but you find hydrogen bonds between the water molecules. And so we have a picture of that here. And so we have the individual water molecules here, which I'm kind of circling here. But then you see these interactions between the hydrogen of one molecule and the oxygen on another. Those are the hydrogen bonds. They kind of weakly link these water molecules together. So apparently you only have enough energy when the water is at 100 degrees Celsius for you to be able to break all those hydrogen bonds and release all the water liquid molecules in the gas phase, or at least enough liquid molecules into the gas phase such that the gas phase is 760 millimeters of mercury, which matches atmospheric pressure, which is 760 millimeters of mercury. Okay, finally, there's one thing I want you to know. I want you to understand, why is it when you go to higher elevations on Earth that water boils at a temperature less than 100 degrees Celsius? And so let's say you went to Denver, Colorado. What you would find is that the water on a typical day in Denver, Colorado does not boil at 100 degrees Celsius. In fact, it boils at a lower temperature, 93 degrees Celsius. And so the question is why? So maybe one of the things you might remember is that water boils when the vapor pressure of the water is the same as the atmospheric pressure. Now, the thing is, no matter where you are in the United States or throughout the world, the water vapor pressure curve pretty much looks the same. But what can change is atmospheric pressure. Now, maybe one of the things you know is that Denver is called the Mile High City. And the reason why it's called that is because it has a relatively high elevation. It is 5,280 feet above sea level. And so when you're at that high elevation, air pressure is not at 760 millimeters of mercury. As you go up in elevation, air pressure starts dropping. So by the time you're at the elevation of Denver, you're at 630 millimeters of mercury. And so now what we can do is we can predict from this water vapor pressure curve as to when water boils, when the pressure outside is only 630 millimeters of mercury, which will be the case on an average day of Denver. So here we have approximately a water vapor pressure about 630 millimeters of mercury. I'm going over the curve, I hit the curve, and then I go down and see what temperature that is. And that temperature is, again, about 93 degrees Celsius. So thank you for listening to that, and we'll see you next time.